So today, the idea of this was that attitude and orientation are really interesting topics in robotics that are oftentimes not described super well by people and not really well understood. So if I could get like a general idea of, and you can like raise your hand or whatever, but how many of you have taken a class where you've done something with attitude, whether it's a rotation matrix or quaternion or Euler angles or something? That'll help me give me some idea as to how I should kind of frame these things. Let's see, a few hand raises. So I'm gonna basically everything I'll go through today, you don't have to know any of this, right? So if this is the first time you've seen it, you may not pick it up on like the first go around. You may have to go, you can either like watch this again or go through the PDF and stuff. But the idea is that this should be like an introduction to attitude for those that have never seen this before. So if you're in that boat, do not worry. All right, cool. So the first thing I'll get started with is just a general idea of a frame and a vector. And these are like not often, like people don't disagree on these things, but there is some confusion. So in general, when we're talking about a reference frame, these things can be defined kind of however you want to. I would argue that the most practical way and the most common way these are defined is a right-handed orthogonal triad. And all this means is that I have, X, Y, Z. So if you remember doing like the right-hand rule, the idea is that X would be your pointer finger, Y is your middle finger, and then Z is your thumb. So this is a right-handed coordinate system. And the idea is that you want these things to be orthogonal. So all these things are 90 degrees apart from each other. So when I take the dot products of these things with each other, they all end up being 0. And you can, if you wanted to, set up your basis to be something else. And that's common in other domains. For everything involving orientation, we'll always assume that this frame is a right-handed orthogonal triad. Then we have this idea, we have some abstract vector. And so now we'll think about these things in, I guess, a physical sense and less of a mathematical sense. So the idea is that I have a vector, which is just something with a magnitude and a direction. And then what I can do is if I want to like quantize this somehow, I can parameterize it using one of these frames. So if I had this vector A, I could write down the vector A as expressed in the basis n by doing the following. So I just take this A, and I'm going to dot it with each of the unit vectors in this frame n. And the idea is that like now when I'm talking about a dot product, it's not as simple as just like, take like the inner product of two vectors. It's like a little more abstract where I'm thinking about if I were to take the dot product of like a C and a D, what I'm really doing is this should be the norm of C times the norm of D times the cosine of the angle between them. So nowhere here do I need to define these things mathematically. If they are defined in the same frame, then this is just the inner product of these two vectors. But for 1 second, we'll take a step back and think about vectors as more physical quantities than mathematical. So just imagine I can describe any two vectors to you in any way I want to. And if I take the dot product, I'll always get a scalar. And how I get that scalar is the norm of the two vectors and then the cosine of the angle between them. So now I think we have I guess, a general understanding of how, like when we talk about these vectors, where we really want these things in frames. They make the most sense to us in frames. We want to have agreed upon frames and use these things interchangeably. So now we'll talk a little bit about the story of attitude. So attitude is basically our orientation. And more specifically, it's always going to be the relative orientations of two of these frames. And we'll always assume right-handed orthogonal frames. So what's super common in robotics is I'll have a world frame. You'll see this as like N or W or I. And then you'll have some body frame, which will be appended to your robot of interest. So here I have like a quadrotor. Here I just have some basis B on here. What's also common is you could have a robot like Atlas or something that has like 100 frames on it. You'll have like, each joint will have a joint frame. You'll have like limb frames. You'll have sensor frames. So it's common that at the end of the day, the robot will have many of these frames. And this is kind of an argument for like understanding this stuff actually is super important, because if you do have a full understanding of this, then when you think about these systems where there's like a lot of these frames happening at once, the attitude comprehension is like super, super important. So when we think about how can we mathematically describe how these two frames relate to each other? And so I guess what I think is the most natural way to describe these things is with a rotation matrix, as you'll see it called. It's also called a direction cosine matrix. And what this is this is a 3x3 matrix where I'm just going to store all of the dot products. So if you see here, this is my Q and B. This is the notation I use for everything. And I have my nx, ny, and z vectors that span the rows. And then I have my bx, by, bz vectors. These span the columns. And the idea is that this is just a collection of these dot products. And because these are unit norm, or if I have like an a dot b, if these are both unit norm, when I do my a, b cosine theta, I end up, these are 1, right? So they don't change anything. So this just ends up being a collection of the cosines of the angles between all of these unit vectors. Hence the direction cosine matrix, or DCM. And I'd actually argue that describing it as the DCM is like a little more, I guess it's less confusing because it reminds people that there's no inherent rotation happening with just a set of dot products, right? I'm just like describing to you the relative orientations of these unit vectors, and there is no like rotation happening. So I think describing it as a rotation matrix kind of confuses people. And if you just think about this as all I'm doing is just storing a bunch of cosines, that to me makes a little more sense. And to get a little more specific about how we actually define this matrix, this is a SO3 matrix. So the S is special. That just means it has to have a determinant of 1. And then O is the orthogonal. So this matrix, the inverse of it is the transpose. So if you'll see here, this is pretty critical. So we have, here's our original matrix. And then this, the inverse of this ends up being just the transpose of this. And what that means is that if my matrix is NB, I can just transpose it, and now I get Bn. So this will be super useful. And this makes sense when we look at it, because if we look at how we constructed this, we have all the n's across the rows, b's across the columns. If you think about it, this were b to n opposed to n to b, I'll just switch the order I did everything, which is the exact same as me doing a transpose. It's also another cool thing to note is that if I think about what these rows and columns actually are, this column right here, this is the bx vector as it's expressed in the n frame. This would be, the ny vector as it's expressed in the b frame. So you can pull out the unit vectors in the opposing frames definition just from the rows and columns of this matrix. And then how do we actually use these things? So what we'll say is that I have some abstract vector A, and I have it expressed in n and expressed in b, and this is their formal relationship. And this is useful because if I have this vector A and it's expressed in b, I can use this rotation matrix to get it expressed in n, and I can just transpose it to do the inverse. So this is kind of like where all this stuff is going to become more important. If we think about like why this is the case, if you go back to our original description of this thing, I have A dotted with all of these unit vectors. So if A is expressed in n, then it's simply just A dot with nx, ny, and z. And if I take this and plug this directly in to this multiplication right here, what you see is that all these dot products end up lining up. And if they're orthogonal, it goes to 0. And if they're the same vector, it goes to 1. And so if you like write this out by hand, which is not that hard because it's only 3 by 3, if you write this thing out by hand, what you'll see is that this A, which was previously dotted with all n's, once I multiply it by this thing, I end up with A dotted with all the n's, which is, I think, a pretty cool way to interpret it. All right, so now we can talk about how we use, multiple of these. So it's super common that we'll have, a few different frames going on in our system at once. So how do we kind of like chain up these orientations? And one thing we got to remember is that if I take the transpose of some series of matrix multiplication, I just flip the order of everything and then add a transpose. So ABC becomes CBA, and they're all transposed. And it turns out this is all the same for these rotation matrices. Here I have, QND is just NB, BC, CD. And the idea is that you got to like link up, you got to match these. So if I'm chaining up a bunch of these matrices, I have to match basically like what the inner frames are for all these things. And that's why I think that if you write them out like this, it makes things a little bit easier because now like they're next to each other. There's another convention that's really popular that I dislike where it will say like D2N and B2C and stuff like that. And it basically like visually makes it much easier to like miss a bug in the code. So yeah, I'd always recommend doing things in this kind of notation way. Now, if instead of Q and D, if I wanted the opposite rotation, if I wanted D to N, what I'll do is I'll just transpose this, and you'll see that I'm going to transpose all these things, and I end up with this same sort of relationship I had before, where I'm matching up all of the inner frames in this. So now this next matrix is kind of defined differently by a lot of different people. You'll see this, I'll write down all the different like notations you'll see. So you'll see like people write it skew, you'll see AX like that. You'll even see AX or AX. Basically all throughout orientation, you'll see people use this skew symmetric matrix where I take a length 3 vector and I convert it to a 3x3 skew symmetric matrix. And this like goes by a million different things. There's also in the Thomas Kane books, he uses a tilde. Zach likes using this hat. So like there's no shortage of notation like in terms of how people describe these things. So what we'll do is we'll stick with the hat, but throughout books and papers, you'll kind of see all these things. And what this hat map is really just doing is it takes some vector, A1, A2, A3, and it puts it in a skew symmetric matrix such that it's, 3, 2, 1 with a negative here, and then 3, 2, 1 with a negative here and here. And for those of you that haven't seen skew symmetric matrices, all this means is that there's zeros all on the diagonal. And then if I take A transpose or A hat transpose, it's equal to negative A. Let's go skew symmetric. This is what skew symmetric means. And this is also called the cross product matrix because effectively what it does is it takes the cross product and it turns it into matrix vector multiplication. So before, if I had A cross B, what I could alternatively do is I could do A hat times B, and now I just use matrix vector multiplication, but this is the same operation. And then what we'll also do is we'll define like an unhat, and this is a little less common, but all this will do is this will take a 3x3 matrix that will just pull out the individual components. So A1, A2, A3. So if I give it my 3x3 skew symmetric matrix, it'll pull out what that vector was that just created it. So this hat and unhat thing, you'll see more common. And the reason that this stuff is like interesting is because here is, I guess, another way to write down. So originally what we said about these rotation matrices is that if I have a vector expressed in B, here's my rotation matrix NB, and I can use this to get AN, right? So this is a 3x3 matrix times a 3x1 vector. So this is, super fast to compute. Alternatively, but equivalently, I can also do, I'll write this down just under here. And full disclaimer, this is completely useless, but it shows something interesting. And when we move to quaternions, you'll see a parallel between this and quaternions. So equivalently, what I can do is I can do AN hat equals Q NB AB hat Q NB transpose. So basically here are two totally acceptable ways to take a vector expressed in one frame and resolve it or express it in a different frame. Both these are fine. You would be crazy to use this one, right? This is like much faster and easier to write down, but this one is mathematically also going to be true. And I'm only bringing this up because when we move to quaternions, we'll do effectively this. Like we don't have this option with quaternions. We have to do it this way. Yeah, so I made a note here. Like this is like totally useless. So do not feel like you ever have to do this in your code, but it will show us like a nice property later on. So then I guess let's go into like a more interesting discussion of everything I've described about rotation matrices. They seem very straightforward. We can construct them easily. We can manipulate them. We can chain them up. So why not use this for everything? And the main issue is that the set of 3D rotations has 3 degrees of freedom. So if I give you a rotation or an attitude, and I say you must describe this using only 3 numbers, you always can, right? But instead, in the rotation matrix, we're holding 9 numbers. What that means is that we have 9 numbers with 6 constraints, giving us 3 degrees of freedom. And those constraints come from this special orthogonal. So the determinant equal to 1, matrix must be orthogonal. These present 6 constraints, such that even though we have 9 parameters in the rotation matrix, we still only have 3 degrees of freedom. And I guess there's a larger discussion here about this, but in reality, you don't want to have super over-parameterized states, especially with constraints on the state. This makes everything for motion planning and control more difficult. So while rotation matrices are great and are simple, they're often the wrong choice for putting inside of a state where you're doing anything in terms of control. So I think that's important to keep in mind. So then the question becomes, if this truly is only 3 degrees of freedom, why not just describe every orientation between two orthogonal bases as a rotation? And that's kind of like where we get all of the other parametrizations. So this was a cool result from Euler, where he basically said that between any two frames, there always exists what he calls a simple rotation between them. And what this means is that I think a lot of us are familiar with roll, pitch, and yaw for like aircraft attitude. And what we're doing in this case is that we're doing a sequence of rotations to move from one base attitude to another attitude. It turns out that you can do this, and this is fine. So Euler angles are very common for describing attitude. But what Euler is saying is that I can get from any orientation A to any orientation B using just one rotation. So the idea is that, this is not like the best graphic, but I will like pierce this frame with some vector r, and then I will spin it about that. And this kind of took me a little bit to fully understand it first, but basically, if I take a rigid body and I orient it two totally random ways, there's always a simple rotation that takes me from one to the other. And this is like a cool thing to like try out for yourself, but it's certainly true. And so this leads to the axis angle description of attitude. And while this is that it's super nice, we just have an axis. So this is the r, this is the unit vector that we kind of pierced our object with. And then theta is our angle. And so theta is like how far do we spin using the right-hand rule about this thing to get from attitude A to attitude B. I'll add a few notes about this. So this is super simple. This is super nice. Why don't we just use this for everything? And there's a few reasons. So one, kinematics are awful. So what I mean by this is that if I described my orientation with this axis angle, the kinematics are the function that takes in current attitude and the current angular velocity. This function is horrible. And it goes singular about 0, which makes it like highly impractical. So for any sort of simulation, this is just fundamentally the wrong choice. But for a simple description of a rotation, I think this is like the most intuitive. Second thing is that there's always, or I guess there's infinite, but for any theta less than 2 pi, actually, I'll phrase it this way. So for any attitude, we have two phis under 2 pi. And this is pretty important. So what I'm saying here is that if you think about this in the 1D case, I could, so imagine if I just had like a 1D case, I could rotate, 90 degrees this direction, or I could rotate 270 this direction. And they both can get me from here to there. So with these simple rotations about a single axis, I can always just rotate the supplementary distance that goes for, our case supplementary is 180, whatever the complement is for 2 pi. So I can spin, 350 degrees one way or 10 degrees the other, or 180 one way or 180 the other. But what we're saying is that for a theta less than 2 pi, there always exists two rotations that can get us there. One will be kind of the short way around, and one will be the long way around. Now, alternatively, we could say that, okay, this must be less than pi. In that case, this rotation is unique. There's always one way to get there. And we can do that, but it comes at this cost. Singularity at theta equals pi. What this means is that if I'm actually using this to not keep track of attitude, but to keep track of a rotation, like I'm spinning an object, I really don't want this thing to go greater than pi. Because once it goes greater than pi, I now have multiple different phis that all describe that same attitude. So I guess like the main takeaway from this is that before we were storing a bunch of dot products as our rotation matrix. And now we're saying is that this seems kind of excessive since this is just 3 degrees of freedom. Why not store the rotation that takes us from one frame to the other? And this way we've now entered the world of rotations and we're not thinking about the relationship between these things as rotations. So in the chat, can you please repeat the first point again? Okay, so this first point is that I have yeah, so the kinematics are awful. And what I mean is that I'll expand upon this. Okay. So the kinematics, this is the relationship between the current attitude, the current angular velocity, and the ODE of the attitude. If we think about this in terms of position, it's super simple, right? If we have a position and a velocity, the kinematics there is we just integrate the velocity and it becomes position. It's not that simple with orientation. We can't just integrate this thing up. We have to use a kinematics function that describes the relationship between the current phi and the current omega that gives us phi dot. So when I say that the kinematics are awful, I'm going to say that they're not defined at 0, singular at 180. So as this angle reaches 180 degrees, your kinematics will blow up and you'll start dividing by 0. And it's also pretty expensive and nonlinear. So the axis angle representation is great for a short description, but it's really not the right decision to make if you have to do any sort of simulation. Does that answer your question, Stephen? Awesome. Okay. So now we can talk about kind of how do we go from, all right, I've just told you that Euler said that there's this simple rotation between these two attitudes, but we haven't done anything in the way of actually computing this. So what we'll do now is that we'll use our hat operator and the unhat operator, and then the matrix exponential and matrix logarithm, which are defined in every language pretty much. And what we'll say is that the way that we convert from one of these to the other is using these two tools. So if I have a rotation matrix Q and I want to get to my axis angle phi, what I'll do is I'll take the matrix log of Q, and this will give me a 3x3 matrix. It's skew symmetric. Then I'll use my unhat function to pull out those three components, and that gives me my phi. And then to go the other way, if I have a phi and I want the rotation matrix, I can do phi hat, and then so this gives me a 3x3 skew symmetric matrix. And then I take the matrix exponential of this, and this gives me the rotation matrix. And it's worth noting that there are special So in general, the matrix logarithm and the matrix exponential, these are power series. And inside your computer, it'll use all these numerical methods and tips and tricks to effectively compute these things accurately without, taking this sequence out to infinity. Turns out that in the case of these matrices, so in one case, we're taking the matrix log of a 3x3 orthogonal matrix. In this case, I'm taking the exponential of a skew symmetric matrix. So in these two cases, it turns out they're super efficient closed form versions to do all these things. And this one specifically, this one right here. So you could always do this. This works totally fine to do a normal matrix exponential, but you could use a specific matrix exponential that's designed to handle these matrices. And this ends up being something that maybe you've heard before. This is Rodrigues formula. And what Rodrigues formula does is it tells us that if we're trying to do this operation, we don't have to use a generic matrix exponential function. We can use a specific one that's special cased to rotations, and it's a nice closed form. There's like a few trig functions in it, but it's relatively simple. And it's also worth noting that if this is small, so if I'm taking the matrix exponential of an axis angle that's very close to 0, and what that means is that the norm of phi is relatively small, and the resulting rotation matrix is close to the identity matrix, that if I take that matrix exponential series and I simply just use the first two terms and ignore everything else, what I get is I can approximate it, but only when phi is really small. In the limit, it'll look like this. But this is only if the norm of phi is like very, very small. So like, this is used all the time in filters and controllers and derivations for things when you take them at the limit for when phi goes to 0. So very, very small rotations. In practice for control stuff, this will work like small angle approximation region. So maybe 20 degrees is a good like rule of thumb. All right, so now this brings us to the talk on quaternions. And this, I feel like, is like really not that difficult as far as like the pure complexity of it. Oftentimes you'll see a bunch of really confusing math associated with this that is just not useful when we're just talking about orientations. So as a general mathematical concept, quaternions is the ideas that I have. So for imaginary numbers, I have a real number and I have an imaginary number. For a quaternion, I have one real number and 3 imaginary numbers. So you'll see a little bit run out of space here, but you'll see that you have things like, can I move anything? No. So you'll see that the quaternion is sometimes like Q equals plus something I plus something J plus something K. So you'll sometimes see it written like this. And so when Hamilton like came up with these quaternions, this is how he wrote them. And he wrote down a bunch of crazy, not crazy, but like weird mathy rules for how to actually multiply these things. And he even like in England, he like carved this into a bridge is like the first time he wrote this down, which you can go see, which is cool. So in general, this is like a very weird abstract mathematical concept that if you're just dealing with orientation, we don't have to know anything about. So people get really hung up on this, and it is like cool, interesting, but kind of confusing. For our purposes, when we're just dealing with orientation, we can totally like move through all of this. So just don't even worry about any imaginary number stuff. Everything is going to be taken care of like just within this PDF, and you don't have to worry about any other crazy math ideas. And so what we're doing here is that we talked about before that this axis angle is a really great, simple way to describe any rotation, specifically the one between 2 frames, but its kinematics are terrible and it has a singularity. So the solution to this problem is that we can wrap our axis angle up into a quaternion that is 4-dimensional, and it solves both these problems. So this, again, the rotation matrix was 9 elements for 3 degrees of freedom. So there were 6 constraints. Now for the quaternion, I have 4 elements for 3 degrees of freedom. So there's 1 constraint. And that 1 constraint is that the norm of this quaternion will be 0. Sorry, will be 1. So the norm for any attitude quaternion is always 1. And this kind of leads into like a little more of the math stuff, but I wrote this as R4. Kind of get in your head that we're dealing with a length 4 vector. That's what a quaternion is to us, like in a computer. Mathematically, you'll see this like math blackboard H for quaternions, and then specifically for unit quaternions, you'll see S3. So you'll see these things in papers and stuff a little bit later in this document. Don't get hung up on it. It's just another description of what we're talking about. And the way we break this thing up is that we have a scalar portion. This is cosine of theta over 2. So remember our axis angle, R was the axis, theta was the angle. So cosine theta over 2, this gives us our scalar part. And then our vector part, which is a length 3 vector, this is R times sine theta over 2. And there's a few like really cool properties about this. So one is that if I just take this expression right here and I construct my quaternion from the axis angle, if I get the norm of this, no matter what R and theta are, as long as R is a unit vector, this will always be unit norm. So by construction, this quaternion will have a unit norm. The next thing is that the positive and negative versions of this. So before I talked about how, I can spin an angle greater than pi in one direction, or I can spin an angle less than pi in the opposite direction. And I can always recover the same relative orientation of these 2 bases. This is true with axis angles. In quaternions, this ends up being the positive and the minus. So what we can do is that we end up seeing that for every attitude, there's 2 quaternions that describe it. There's Q and there's minus Q. And these describe different rotations. One goes greater than 2 pi, one goes less than 2 pi. So they describe the same rotation, or sorry, the same attitude, but they're different rotations. And so one of these, so Q or minus Q, one of them will have a positive scalar. This indicates just by looking at cosine of theta over 2. So the one that has a positive scalar, this means theta is less than pi. And if the cosine theta over 2 is negative, it means theta is greater than pi. So it looks like someone raised their hand, so you can feel free to speak up.
Yeah, you mentioned that quaternion has a 1 degree of freedom and axis angle has 3 degrees of freedom.
So a quaternion has 3 degrees of freedom, but 1 constraint. This is the constraint.
So ultimately it has 3 degrees of freedom.
Yeah.
In the end.
All rotations. So yeah, this is worth right now. I'll do a little section right here. So rotations 3 degrees of freedom. So for a rotation matrix or a direction cosine matrix, this is 9 terms minus 6 constraints, read off. And for axis angle, I have 3 and 3, 3 minus 0 constraints, read off. And then for quaternion, I have 4 terms, 1 constraint, to read off. So all rotations, no matter how you describe them, they will always have 3 degrees of freedom. And if the way you're describing it, using a rotation matrix with 9 terms or a quaternion with 4, you will always have the number of constraints that is the complement to that. So in the terms of the rotation matrix, we had 6 constraints, which brings us down to 3 degrees of freedom. And the quaternion, we had this 1 constraint, which is that our quaternion must be unit norm for it to be describing an attitude. Does that answer your question?
Okay, got it. Yeah, thank you.
Sweet. Okay, so now I'm gonna
Kevin?
Yeah.
I have like 2 questions. The first one is like, why the angle is divided by 2? Is it just the mathematical derivation and then the norm has to end up to 1? And that's the only reason? And the second one is like, is there is this possible to get an intuitive explanation of what is a quaternion? Because I tried, I watched videos with this, I still don't get it.
Yeah, so this is I guess there's like a lot to say about this. So in general, there are geometrical descriptions of what's going on here when I wrap my axis angle in my quaternion. The issue that I have with all those descriptions is that this is fundamentally a 4-dimensional thing. So you're projecting a 3-dimensional vector, which is our axis angle vector, and we're projecting it to a 4-dimensional like hypersphere, which you can't visualize. And so when you watch these videos, they try these crazy tricks to like get you to intuitively understand like the geometry of what's happening. I have never really been convinced by any of those things. I don't think it's that compelling, and it definitely doesn't help you understand it, I feel. So there's a great video by 3 Blue 1 Brown where he does like, I think, the best job at like a geometrical interpretation of what these things are, if you've seen that video. But I did not feel like walking out of that video that I had an inherent better understanding of how these things work. So I know that's kind of an unsatisfying answer, but that's like my personal take on this. And then your first question was to do with the divided by 2. So you're going to see 2s show up everywhere in quaternions, and it's like a little hard to explain like how they end up there, but they all generally have to do with the fact that we have what's called a double cover. So that's this right here. And what this means is that every attitude I can describe with 2 different orientations. 2 different rotations. So Q and minus Q both describe the same rotation. The same attitude. So Q negative Q, same attitude, different rotations.
Okay.
Same attitude, different rotations. And then you'll see this called everywhere as the double cover. And they call it the double cover because basically the space of unit quaternions, so S3, it covers the space of rotations twice. That's where we get the double cover.
Okay.
All right, so now I'm going to go into, I guess, the quaternion math. And what I'll do is I'll write out just at a high level, like the elementary quaternion operations that we're interested in. And then in red, what I'll do is I'll write down these same operations, but with a new set of notations such that we can do all the quaternion stuff using just normal linear algebra. So I know for someone like me who's done like a little more linear algebra stuff, that it's nice to see everything in all of my equations be matrix math and don't have any weird like quaternion stuff showing up there. And Zach definitely prefers this. And a big reason is that when you take derivatives, you can take all your same derivatives by using normal like matrix calculus tricks if everything's written in linear algebra, but it's more difficult if there's like weird stuff going on. So this will become a little more clear in a sec. So the first thing is that when we took our rotation matrices, I said that we can chain these things up using matrix multiplications. So imagine if these were all, this was big Q, this was big Q, this would be a matrix multiplication right here. But what we're saying is that we have a quaternion multiplication, and this is called the Hamilton product. And again, the notation is all over the place. So you'll see this right here, you'll see this thing. Sometimes you'll just see just like multiplication. And so it's really important for you to actually look at like whatever this paper or code or whatever is doing and figure out like what they're talking about, because there are different versions of this. But we're going to stick to what's called the Hamilton product. This is like the original quaternion multiplication. In our set of conventions, this is what makes everything work. So try your best to ignore the horrible notation everywhere. So what we're saying is that we can multiply these things together, right? Just as a concept, I can multiply quaternions. And what this means is that, this is unit norm, this is unit norm, this is unit norm. So it's closed under quaternion multiplication. If I multiply two quaternions that are unit norm, I get a unit norm quaternion. And so the way this looks is that if I think about these two quaternions as their scalar and vector components, so each one has a scalar, this is S1, S2, then I'll have a vector component, V1, V2. When I multiply these things, I'm going to create a new quaternion where the scalar part, I'll write this out. The scalar part is just S1, S2 minus the dot product of the vectors. And then the vector part is the S1, V2, S2, V1 plus the cross product of these. So when you see Hamilton in like the original quaternion stuff, he writes out like the imaginary number math of like, what's I times I, what's I times J, what's J times K. All of that logic is captured right here. So this is basically what lets us not worry about the hardcore imaginary number math stuff and just think about this in terms of all these operations that we're already familiar with. So then the question becomes, can I rewrite? So what I can do is I can always just write a function that is just quaternion multiplication. It just takes in two quaternions and spits out another quaternion. I can write that function. That's totally fine. In fact, that's what I prefer doing. Alternatively, this is where I'm going to introduce the red notation. We can write this thing down as a matrix vector multiplication. So if we take this right here, which is our quaternion multiplication, and I basically just do some rearranging because this is bilinear. So basically every term has, every single term in this thing, it has an element from one quaternion and an element from the other. So it's entirely bilinear in these two quaternions. So what I can do is I can separate them and I can write this down as this matrix times the second quaternion. So you can go and you can like work this out on your own. And this matrix we'll call L of Q. And what L of Q does is it lets us do quaternion multiplication. So we'll do is we'll define this L of Q function that takes in a Q and it spits out this 4x4 matrix. And what this lets us do is we can now do quaternion multiplication using just matrix vector multiplication. I can do the same thing, but I can separate out the other quaternion. So I can do, opposed to having the second quaternion here, I can have the first quaternion here. And this gives you my R matrix. And the only difference you'll see is that opposed to a plus here, you have a minus. And this comes from the cross product, because remember, if I flip the cross product, it's the same as negating it. So A cross B equals negative B cross A. Otherwise, these matrices are the same. And so a few cool properties. So the first is that these matrices are orthogonal. So L of, and we haven't gotten to the quaternion conjugate yet, so just ignore this for a sec, but L transpose equals L inverse, R transpose equals R inverse. And what this lets us do is this lets us say, I can do this, where I write down the quaternion multiplication in quaternion math, and this is fine, but this looks kind of weird amongst other normal math. Or I can use these matrix functions that I've just described, and I can do this. I can do L of Q1, Q2, and this is like what I like using for all the derivations. Or if for whatever reason I want to separate out this Q1 and put this on the right, I can do R of Q2, Q1. So does this make sense, like kind of where the L and the R came from and how like it could be useful to have Q2 on the right or Q1 on the right, and how I can use L or R accordingly to move whichever quaternion I want to move to that one side? The next thing is the quaternion conjugate. So with rotation matrices, we said that if I have Q and B and I want Q, B, N, I can take the transpose of this, and this gives me that. So we can't transpose quaternions, we can conjugate them. This is kind of the quaternion version of this. And all this does is it's written with this dagger symbol, and you'll see this written a few different ways. Sometimes it literally is looks like a dagger thing, which you'll see like in like LaTeX, dagger. And a quaternion conjugate is just all it's going to do is going to flip the direction of the rotation. It's going to do so by just flipping the vector component. So it takes my what was scalar vector, and now it's scalar negative vector. So this is the quaternion conjugate. And what I said earlier is that you can also do all the same stuff using just matrix math. So I can have this matrix T all defined, and all T will do is when I multiply T times this, it's the same as the quaternion conjugate. And another cool thing about my L and R matrices is that if I want to do L of Q conjugate, I can just do L of Q and then transpose it. So this lets me use all my same transpose tricks. So I guess hopefully it's making sense now why we like using these LRT matrices. It's because they make stuff just a little cleaner and more recognizable when we write down the actual math. And then the last thing we'll define is for rotation matrices, we have the hat map. This is where I take a length 3 vector and I convert it to a 3x3 skew symmetric vector. And what we'll do here is that we'll define post a hat. We'll do a hat plus a bar. And what this will do is this will take a vector and it'll convert it into a pure vector quaternion, as it's called, which is just a quaternion. So it's a length 4 vector. It has 0 for the scalar. Then it has whatever vector we input in as the vector part. And this is going to show up everywhere as well. And again, we can write this down using our red terms. Remember, this is our like writing down the quaternion stuff in matrix math. So I can have this H matrix, and H will take a normal vector and it will convert it into this. And we can also do, write this down. I can do the unhat thing. Yeah, I have it right here. So I can do this same operation for the hat map, and I can do it in reverse. So I can take a quaternion and I can separate out. So this unhat map will just take the vector components. And this is the same as me doing H transpose Q. So these two things are the same. Unhat. Okay, so this right here, I just laid out quaternion multiplication, the conjugate, the pure quaternions, the hat map. This is all we had to know about the elementary quaternion operations. So we know these, this is all we have to know. So now what we can do is we can do something pretty cool. We can look at all the stuff that we know about rotation matrices that we showed earlier, and we can just write them down in terms of quaternions, and we see that things are like almost identical, right? There's this great symmetry between these things. The first thing is this was admittedly a useless way to take a vector expressed in one frame and write it down in another. This should be n. And then this same operation here, we can do it in quaternions. And where we had matrix math here, we now have quaternion multiplication. And then where we had the hat map for quaternions, we see we have the normal hat map for skew symmetric matrices. And we have a transpose here, we have a conjugate here. So there's, for each of these corresponding groups of rotation matrices and quaternions, we defined all these operations and we see that they match up between them. So where I'm multiplying matrices in rotation matrices, I'm using quaternion multiplication. Where I'm transposing in rotation matrices, I'm doing a quaternion conjugate. And then when I do this hat map, I have my quaternion hat map. So there's like this great like symmetry between all these things. The next thing is how we kind of chain up these rotations. So, you know, we just write things down like this. This is just normal matrix multiplication. And we can do the same thing in quaternions, but this is now quaternion multiplication. And then the transpose is just me doing my quaternion conjugate. And then one thing that we probably won't go into today because we don't have time, but this is the kinematics of the attitude. So what is the time derivative of this attitude with respect to the current attitude and the current angular velocity? So we'll see, we'll prove this in a little bit. We'll see that this is what we have for rotation matrices. This is what we have for quaternions. And this lets us simulate how these things move as quaternions, as like attitude parameterizations. And we see that these things are pretty much the same. So hat here, hat there, matrix multiplication here, quaternion multiplication there. The one thing that's different is that we have this rogue 1/2 show up. And this is, you'll see this everywhere. This is, again, it's all has to do with that 1/2 you saw in the original description, the idea of like the double cover, and you'll get these 1/2 showing up everywhere. Now, equivalently, I can write these things down using just the red notations, like all the matrix math notation. I don't have to use the specific quaternion stuff. So this is equivalently written as this. And I won't, you can go through and look at this on your own time, but basically what I wrote down here in terms of the, elementary quaternion operations, I wrote down here using all the normal matrix stuff we like. So, here are our kinematics. And then we can use this real quick to show how do we get, if I have the quaternion, how do I go from quaternion to rotation matrix? And so let's take a look at the original equation we had, which is how we move a vector that's expressed in B and express it in N using quaternions. And so what we have is that we have quaternion multiply, hat map X, multiply, conjugated this. And so what we'll do is that we'll just go through and we'll swap in all of our matrix stuff. And this lets us move everything around. So this first multiplication of this times this block, I can do as L of Q. So yeah, where you see the Q's here, this is Q and B. So this times all of this is LQ times this. And then if I look at this chunk right here, remember I can use my R matrices to take the quaternion on the right side and represent it as R of the right-handed vector times the left-handed vector. This gives me R of Q transpose, because it's conjugated, times H, this is our hat map, times XB. So this is equal to this is equal to this. And this lets me get this new expression where if I do H transpose on both sides, I get XN equals this big block right here times XB. What we see is that this block right here is a 3x3 matrix, and this ends up being our rotation matrix. So the way that we start with a quaternion and get the rotation matrix is just by using this right here. And then again, there's like maybe 5 common ways you'll see people compute this. This is like a little more obscure, but it matches all of our notation, and we're not that worried about speed.
Kevin, so in simulation and other software, if they use quaternions internally, they always like get those direction cosine after, right?
Yeah, so I think is like the best way to do it is what I'll have is like the actual, like the ODE being simulated. So say I have like a rigid body, I'll have like position, velocity, quaternion, then angular velocity. And I'll use this in my state and I'll simulate everything with my quaternion kinematics. And then when I go and actually compute stuff like sensor measurements or any like realistic geometry thing, I just convert it immediately to rotation matrix, right? Because in my eyes, using rotation matrices are super easy and they make sense, and everything is well defined. So to me, it's easier to just take. Okay, so he's got a good question here. Can you explain a bit how angular velocity is usually represented? Yes, this is a great question. So actually, I'll go into 2 things about this. So the first thing is that before I said this is the most common thing we'll see in spacecraft and robotics. So if I have some robot here, if I have this right here, so I have some world frame N, then I have some spacecraft or quad rotor or robot body frame B. If I were to put a gyro on this, what I would get is this is what the gyro would read. It would read omega. This tells me what is the angular velocity of B in N, and then expressed in B. So this is almost never written out with this full notation. People just write omega, and you're just supposed to assume that they're talking about what you think they're talking about, and they almost always mean this. So when they say omega, whether it's a spacecraft or a robot, they're almost always talking about the angular velocity of the body B with respect to some inertial frame or world frame N, and then it's always expressed in the body frame of the robot. So again, if I had a gyro and a drone, this is what I'd be talking about. Does that answer your question? Sweet. And then the next thing that's worth talking about is that when I actually go and simulate these things, so I wrote down, sorry, go ahead.
The follow-up question, like, is it a convention thing or is it like needed for this kind of application, the omega that needs to be expressed in the body frame? Like,
so so in general, this is what a gyro gives you. But it's kind of basically we chose the convention to match the fact that the gyro gives us this. So in its most generic terms, I can write down this. QNB dot equals Q and B, and then omega N, B, B, hat. So I can write this down in whichever way I want to. I've made no assumptions about what N and B are. It's not like one has to be inertial and one can't. For any two frames, N and B, the kinematics of this rotation matrix between them, it will evolve like this. And so because we write down because we always have this sensor measurement, this is like what our gyro is. It makes the most sense to think about everything in this, I guess, notation. But you don't have to. You could do other things. So you could equivalently write this thing out with like an N right here. That'd be fine. It'd be like annoying, but you could do it. Yeah, so you have a lot of options. This is the one you should almost always use.
So when we write the equations for dynamics, we have a body frame attached or a world frame attached. So when we have this kind of a situation, like do we have multiple, like do we have to deal with multiple frame of references, or like how do we deal with like a single equation with only one frame of reference?
So we have a generic world frame. This is like some N. So if I'm like, moving a quadruped in a room, N will be somewhere fixed to the room. And then what I'll have is that I'll have, depending on how I describe the dynamics of my quadruped, I'll have either like a floating base, like the center of the quadruped, and that will be my body frame B. And then maybe I'll have a new frame for every leg. And the kinematics for all these things can be expressed with this right here. So I can just substitute in what the actual frame of interest is.
Okay.
Does that answer your question?
Yeah. All right. Thank you.
Cool. And so another thing that's really worth noting, which is another compelling reason for us to use quaternions. So before I talked about how rotation matrices are great, but they use 11 parameters and there's 6 constraints, so it's a little overboard. Another reason this is difficult is because if I go in a computer and I simulate this with like RK4, what I'll get is that over time, due to numerical round-off error, I will drift away from orthogonality. So it'll start as a perfect SO3 matrix, so it has determinant equal to 1 and it's orthogonal. And as I simulate this thing, if it was perfect integration, it will always stay on this SO3 manifold. But in reality, it will end up moving away from the manifold. So a little drawing of this, I can have, here's my SO3. And as I integrate this thing, it's going to slowly drift off. And what I can do is I can re-orthogonalize this, right? But this requires me computing an SVD, which is pretty expensive. So I can do, compute SVD, and this will put me back on the manifold. And then I can, keep going. So you can do this. This is totally fine. It's just really expensive and kind of annoying. Alternatively, if you're doing quaternions, you get the following. So for a quaternion, I get my manifold is unit norm. And so when I go and simulate this thing, I will drift away from unit norm a little bit. And to put myself back in the manifold, all I have to do is normalize. So normalizing a 4-dimensional vector is way faster, like probably between 100 and 10,000 times faster than me doing the SVD of a 3x3 matrix. So as far as what it takes, what it costs us to project us back onto that manifold such that we're like in the safe space again, is dramatically cheaper for quaternions than it is for rotation matrices. Does that make sense? I'll say quats DCMs. This is another reason that we love using quaternions. All right, now we'll talk about a Rodrigues parameter. And this is basically a clever way for us to think about a quaternion, but only worry about 3 parameters. So if you imagine if I told you that, all I need to know is the scalar and the vector parts of this quaternion. And if I know it's unit norm, then I should be able to reduce that information down to a 3-parameter thing. And you can. And so this is a Rodrigues parameter is just going to take the vector and divide it by the scalar. So this is my Rodrigues parameter from a quaternion function. This will take in a quaternion. It will separate out the scalar and the vector parts. It'll just do vector divided by scalar, and it'll give me my Gibbs parameter G. And then what we'll say is that, we mentioned before that Q and negative Q, they both describe the same attitude. And the cool thing is that G, the Rodrigues parameter, doesn't care about this, right? If I do V over S or negative V over negative S, it ends up giving us the same G. So for all, and this is worth noting, this is still So just like the axis angle, still singular at 180 degrees. So we're back in this territory where with quaternions, we can simulate wherever we want to. We'll never hit a singularity. It will just simulate forever and be totally fine. If I were to try to simulate my system with a Rodrigues parameter or a Gibbs vector, I would explode once I reached a rotation magnitude of 180 degrees. So this thing is singular at 180. But it's great for doing small stuff. Go ahead.
Yeah, I mean, you can answer. It was like, for what purpose would you use that parameter?
So this is very common to be used both in controllers and filters. So if I'm doing some estimation and I have like an error state, like in a Kalman filter, there's a version of the Kalman filter called the multiplicative extended Kalman filter that will do exactly this. It will treat the error state between my prediction and my measurement as one of these small 3-parameter things, like an axis angle or a Gibbs vector. And it's great for that, but it's not good for simulation. Like you should not use this to simulate your system. And also it's used in controllers. So like what we'll do in this class the next few weeks is that we'll talk about a way to do like motion planning and control on things with quaternions. And the actual like feedback controllers that we're going to develop are going to work on an error state. And this error state is going to be defined with something like a Gibbs vector.
Okay, thanks.
And then we have it's called the Cayley map. And this is the way that we can go. So we define up here is how do we get a Rodrigues parameter from a quaternion? And this is how do we get a quaternion from a Rodrigues parameter? And it's super simple. We just normalize we normalize a 4-dimensional vector where 1 is the scalar part and G is the vector part. So super straightforward. This is what we'll need to know about Rodrigues parameters. All right, so now I think we're doing pretty well on time. The next 20 minutes, I'm going to go through how do we optimize over attitude. So in general, nothing we've done so far in this class have we had to optimize over things where our primal variables have intrinsic constraints on them. So what we've done is that we've done things like, well, we'll optimize over a constrained optimization problem. So I have some cost function and some constraint function. It's weirder now because we now have elements of the state that must explicitly like satisfy these constraints, which is something we're not used to doing. So what we did is that we went and developed like a kind of different way of thinking about these things and like modifying our tools such that all the stuff that we've, grown to love using in this class will all just kind of work for quaternions once we make these small adjustments. So the first thing is that we like thinking about things additively. We write these deltas, it's always x plus some delta x. We have like a step update, my xk plus 1 equals xk plus delta x. We love adding things, right? This is what makes the most sense. But this doesn't quite work for quaternions. And the reason why is because I can't just write down like a q plus some delta q, because this delta q doesn't really mean anything unless it's unit norm. Because we said that in order for a quaternion to describe an attitude, it has to be a unit norm. So if I have some delta q and it's like, a small, like the same way this delta x dx could be small, this is just some small vector. It's not unit norm and it doesn't really mean anything. So it's like mathematically incorrect for us to think about these deltas as delta q's. But the problem is that the way that we look at Taylor series is that we're always adding stuff. And so what we do before is that we did x plus delta x. So this is an additive update. What we're going to start doing for quaternions is we're going to do a multiplicative update. And what this means is that opposed to doing q plus delta q, we'll do quaternion multiply. So left q times quaternion from MRP, or sorry, from quaternion from RP of our Rodrigues parameter G. And so I'll go ahead and spell this out again. So, add would be x plus delta x. Then our multiplicative update is going to be q with, quat from MRP G. So now opposed to just having a delta and just adding it to our existing value, we're going to simply compose rotations. So we can't just add quaternions. Like nowhere in what we defined in our elementary operations did we add things. So nowhere in rotation matrices can you just add 2 rotation matrices. They'll end up not being orthogonal. And the same is true with quaternions. We can't just add these things. So it doesn't make sense to set up our problems where we're like adding these updates onto Q, because Q will end up not being a quaternion because delta Q is not a quaternion. So instead, what we'll do is that we're going to apply these updates and think about these deltas with respect to multiplication, and this is quaternion multiplication. So before it was x plus delta x for all of our normal stuff that we've done, and now we're going to update these quaternions by we're multiplying it with a small rotation. So we're just like rotating the attitude a little bit. And the thing is that we set up Taylor series such that we're adding stuff, right? This is like kind of like how we defined everything is we have like our current value of the function plus a Jacobian times a delta. Like we're always adding stuff. So if we already know that this is how we want to write down our updates, then we can modify our derivatives in our Taylor series to account for this, such that even if we're adding, we're still kind of multiplying them. So this will seem like kind of a weird idea, but we'll do a quick example that I think will clear it up. So if you imagine if my update, my delta is small. So before I had delta x, now I have g, this is my delta. So if g is small, when I do this update, which is, quaternion multiplication of q times this quaternion that comes from this small rotation g, for very small g's, this is approximately doing this. So remember, if I take the Cayley map is what takes me from a quaternion, or takes from a Rodrigues parameter and gives me a quaternion, and I have to normalize it. So let's assume that we're close enough that this thing is close enough to 1. So for very small g's, this is an okay approximation. And in the limit, this is exact. Like as the norm of g goes to 0, this is what it will look like. And so we can write this out as this is, again, approximately. I can just separate out these two terms. So I have LQ times just the identity quaternion, so all ones, or sorry, 1 with 3 zeros, and then LQ times H times G. And so what we've done here is that we kind of showed that we can do the additive stuff, but we can't just add G onto Q. We have to push it through this LQH stuff. And what we call this is that we'll call this G. And this is what we call the attitude Jacobian. And this is what you'll see Zach call this. And basically what we did is that we showed that I can actually add these things. I can add a G to a Q, but only if I first push it through this matrix right here. So now what we're going to do is we're going to use this logic and we're going to apply it to our Taylor series, and we're going to modify those derivatives such that opposed to having a normal Taylor series where I'm multiplying things by a delta Q, I'm now going to add these things with this special attitude Jacobian there. So another perspective is that if I were to take a function f right here, and this is just a normal, takes a normal x, outputs something normal, like say they're both vectors, the Jacobian, if I had this delta x term and I evaluate this derivative as delta x goes to 0, this is the exact same as just my normal Jacobian of df dx. And what we said is that now that we're doing things kind of differently, we're doing these updates in a different style than we were doing before. We're now doing them multiplicatively. What we get is that if I take the derivative of this right here with respect to some g, as g goes to 0, I now get my original matrix, df dq, my original Jacobian, and then I have to append this g on the right-hand side. So this is another perspective as to where this g comes from. And basically just, again, this is, I take my derivative that is, thinks about quaternions as just normal 4D vectors, and I use this g to kind of convert that one dimension down by 1, such that I'm now thinking about Rodrigues parameters. So the first thing we'll look at is here is a Taylor series for some function where I take in quaternions. So remember, h is unit quaternions, or h is just any quaternions. So say I take in an h and I output some vector. And so say I want the Jacobian of this thing, I take this right here, which is how I apply this update. And what this gives me is that I have f of q, so the current value of the function f, as so if g is all zeros, then this is the identity quaternion, and LQ just equals q. So I have the current value of it, just like a normal Taylor series. And then opposed to having, df dx plus times delta x, I now have df dq, and then I modify this Jacobian with my G matrix, my attitude Jacobian, and then now I can just use my G's as my deltas or my arrow states or whatever you want to call it. And so here is that this just means that we're going to modify all of our Jacobians with these G's, and we're just going to, for Jacobians, just shove the G on the right-hand side. And now, opposed to thinking about things in terms of delta Q's, we're now thinking about, which is a 4-dimensional quaternion, which is not really real. We're now going to think about things in terms of the 3-dimensional G, which when it's not unit norm is still well-defined and everything. So the first thing we'll look at is how do we do Newton's method when we're describing our Jacobians like this. And this is kind of like the start of how we're going to optimize over these things. So if I have some function f of q and say this is outputting some vector, so the Jacobian of this thing is going to be, it's going to have 4 rows, or it's going to have the number of rows as outputs, the number of columns as inputs. So we'll have 4 columns. So if I want f of q to equal to 0, the way I'll do Newton's method, it's going to look super similar, but with 2 slight changes. So this residual function, I compute it the same way, no changes here. When I compute the Jacobian, now I see the first change. So this Jacobian is, opposed to just doing, the normal Jacobian of df dq like we would for a normal Newton's method, I now take my Jacobian and then I modify it with my additive Jacobian. So I take this G matrix, I shove it on the right-hand side, and this changes my dimensions such that I'm now thinking about things in terms of 3 parameters, not 4. Then I solve this G, and this is going to give me a 3-dimensional Rodrigues parameter that defines my step. So before I had delta x, now I have G as my step direction. And then I do some line search on alpha. And the way that I apply the line search is I have L times QK times quaternion from Rodrigues parameter alpha times G. So to the left here, I'll write down what normal Newton's method would be. So if this was f of x equals 0, this was normal Newton's method, I do the following. I do res equals f of x, jack equals just the normal Jacobian, delta x equals negative jack res, alpha equals line search, and then xk plus 1 equals xk plus alpha delta x. So here we kind of see that here's normal Newton's method. And what we've done is that we've modified this thing right here. We've modified our Jacobian with this G matrix. And then we've modified how we apply the update. So before we just apply these updates additively, now we're going to define them using quaternion multiplication. And this is pretty much it as far as like how we modify Newton's method to handle quaternion inputs is we just apply this G here to modify the Jacobian, and then we just change the way that we update it. And this just makes Newton's method work. So one thing I feel like I didn't go over that's probably important is the dimensions of everything. So before, when I said that we have some function f that takes in a quaternion, outputs some vector. So if we imagine what this Taylor series looks like, is I have f of q, this is a length p vector. Then I have my normal Jacobian, which is p by 4. But remember, I don't want to think about things in terms of the 4-dimensional delta, because that delta q means nothing. So I modify it with this g, which is 4 by 3. This basically takes a number of columns from 4 columns down to 3 columns. And then this G right here is 3 by 1. So the dimensions kind of screw some people up. So I just, in a few places in this document, I wrote down the dimensions of everything. All right, so here is modified Newton's method for this. And since kind of run out of time here, I'll do, I guess, relatively quick through the rest of this. So the next thing we'll look at is what we do with the quaternion valued function. And all this means is that, so this is not the value function, like the cost to go function. This is just a quaternion that takes in a quaternion and outputs a quaternion. And so what we do here is that the way that we modify this Jacobian is that we assume that this function has, q prime is the output of fq. The way we modify this Jacobian to think about things in terms of this Rodrigues parameter is we basically like smush it together with 2 G's. So on the right-hand side, we have GQ. We've seen this before, and this is kind of the way that we like condition the input. So opposed to inputting in delta Q's, this lets us input just the Rodrigues parameter. And then on the output, we have to then convert what would have been a 4-dimensional like change in DQ. We're now going to convert that back down to a 3-dimensional thing. And this uses the G matrix again, transpose, but this is G prime. So this quaternion is the output of our function f of q. So for a function f that takes in a quaternion, outputs a quaternion, the way that we modify this Jacobian is we sandwich it between these 2 G's, where on the right, it's the input q, on the left, it's the output q. Next thing is what to do for a Hessian of a scalar f. So the Jacobian case, that would work for a gradient as well. No issues there. But the Hessian case is more interesting because we now have like one other term. So you can go through and you can draw this by hand. It's actually like a good exercise, I think. But we'll see is that this is our original Hessian. So I modify this by doing GQ on the right, GQ transpose on the left, minus a 3 by 3 identity matrix. And then I have this scalar here. And this is the dot product between our quaternion Q, and then the gradient of this function f with respect to that quaternion. So the reason that we're doing all this stuff is that we can get these derivatives using forward diff easily, right? There's nothing crazy about getting these derivatives. So we can do is we can get these derivatives with auto diffing, and then we can modify them with these additive Jacobians and these tricks. And we can use them now with our three-dimensional arrow state. So our Gibbs vector or our Rodrigues parameter for everything. And it lets all this stuff just work much better. So as a general review of the stuff that we just went over, so we went over three specific cases. So the first two were Jacobians. So this is quaternion in, vector out. This is how we modify the Jacobian. We append the G on the right. And then for quaternion in, quaternion out, we smush up between these G's, where this is the output quaternion, this is the input quaternion. And then for the Hessian, we do something very similar as we do for the second case here. We have G transpose G, and then minus this term over here. So these are the three tools that you'll need to know as to how to modify these things to work with Newton's method. And I just showed an example of how it worked for a general root finding problem. Now I'll look at if we wanted to do optimization, like unconstrained optimization over some function, how do we do that? So if I want to minimize over quaternions over some scalar cost function f of q, what I'll do is I can use Newton's method and I can use all the tools I just described above. So here's my, this first thing will take a little bit of explaining, but in general, what we said is that if I want to modify df dq, I got to do df dq gq, right? But unfortunately, due to the conventions, the gradient of this function is going to be transposed, right? That's the gradient like nabla q of f, because we want this to be a column vector. This is going to be df dq transpose. So the reason that this first expression looks a little weird with all the transposes is just to make the dimensions work out, because our gradient by convention is going to transpose this thing. So I wrote this out in blue, but just so you know, looking at this is kind of where the transposes come from. So our modified gradient is going to have, this is our Jacobian. So our Jacobian, we throw the G on the right-hand side, and then we'll just transpose it again since we want this gradient to be a vector. So these two T's, they come because we want our gradients to be column vectors, and we convert them by like to and from this by using the transpose. The next thing is our modified Hessian. So this is the third equation we went over. So here's our normal Hessian that we get from auto diffing, and then we smush it between these two G's. Then we have this other term right here, and then now we have our grad and our H. We compute our step G. We do whatever line search we want to on alpha. And then we update our parameter by doing qk plus 1 equals the exact same as before, quaternion multiplication of q times quat from Rodrigues parameter times alpha times g. And this is super important. So the reason we do this is that this will always return a quaternion. This is normal quaternion multiplication with two unit norm quaternions. It will result in a valid unit norm quaternion, even if this alpha is less than 1. So if this alpha is like 0.1, it just means this is a small rotation, which just means that the resulting quaternion is pretty close to identity. It's a small rotation, but it still preserves everything. It's still unit norm quaternion, unit norm quaternion. And then something that is, I totally forgot to mention, but is critical, and I'll add this to this document later, is they have these identities where if there's no rotation for a rotation matrix, this ends up being the identity matrix. And if there's no rotation for a quaternion, this is the quaternion identity. So still unit norm. So a mistake you'll see people make is if people will initialize Q as all zeros, unless Q is unit norm, it's not a quaternion, or it's not an attitude quaternion that describes an orientation. And then the identity, so these are identities. Identity, no rotation. All right, so I think that was a lot. My plan is to upload the video. You guys can go through it, ask me tons of questions. It'll take like a few days of thinking about this stuff to really fully understand it. I would urge you to like go through and like do these derivations yourself. They're like really not that crazy. So two really cool ones to do that I included here is how to get the kinematics from the rotation matrix and from the quaternion. What we'll see is that just like before, the process ends up being the same, but in quaternion land, where we do quaternion multiplication and all those quaternion elemental operations, and in rotation matrices is all just matrix multiplication. So this would be a cool thing to do. I'll upload this. And then ideally, I can't promise this, but I'm trying to like write this all up into a general document because my handwriting is horrible. And then I may upload that like by the end of the weekend or something. So I know that was a lot. Zach will go over this stuff, some of this stuff as well in the next few lectures. And then we'll have like some fun homework assignments where we do stuff just like this. Hopefully this was like a good run through. If you've seen this before, if you haven't, hopefully it wasn't too overwhelming. But yeah, I'm happy to stay on for a while now and answer any questions people have.
I have a practical question. As for every tool, is there a practical case where quaternions are not the solution?
Yeah, so I guess like feedback control is a good example of where you don't want to use quaternions. So, you know, we're so used to doing linear feedback policies. So we like doing, you know, U equals negative KX. Doing things with a quaternion here is really difficult. So we don't ever do linear feedback on the quaternions. What we do is that we describe the error state using this Gibbs vector, and then we use linear feedback, and it works like amazingly. But you wouldn't want to naively use a quaternion for a linear feedback policy. But as far as simulation, it is like, you know, nobody should use anything else, and rarely do people, like, you'll see people use rotation matrices. That might be like the second place most common option, but it's way less common than quaternions.
Okay,